From 7b, we start looking at how we use tools from previous years to generate probability distributions. So in this case here, we're going to generate a probability distribution for x, where x is the number of blue tickets selected. The question is asking 2 tickets are randomly selected without replacement from a bag containing 5 blue and 3 green. Let x denote the number of blue tickets, find the probability distribution. So here we're looking at the outcomes and the probability that those outcomes occur. And the outcomes are how many blue tickets are there. There are either going to be 0, 1 or 2 blue tickets because we're making those selections. And what we're asked to find is what is the probability that there are 0 blue tickets? What's the probability there's 1 blue ticket? What's the probability there's 2 blue tickets? And a useful tool for doing this is a tree diagram. So I thought I would jog your memory of how a tree diagram works.
Yeah, diagrams that are great.
Tree diagram is blue, green. You could also write blue, not blue, so blue and blue dash. And then again, our second choice is blue, green. I was going to write not blue, but green. Blue, green. Then we assign the probabilities. So the first pick, the probability of getting a blue is 5 out of 8 and 3 out of 8. And then what's the probability of getting another blue?
4 out of 8. 4 out of 7.
Lovely, 4 out of 7. Therefore this is 3 out of 7, this is 5 out of 7, and this is 2 out of 7. When we're doing it without replacement, we're happy we adjust the probabilities as we go along. And then we do some good mental arithmetic. What's the probability of ending with a double blue?
20 on 56.
Good, 20 on 56. We multiply those, that times that gets us the probability. So we are looking here at 20 on 56. I'll give you a pro tip, jump to the other end. The probability of getting 2 greens is 6 on 56. Yes. So the probability of getting this can be done 2 ways. You can either do that and add them.
Or subtract.
Or yeah, you subtract. So that's 26 on 56.
30 on 56.
Lovely, 30 on 56.
So you can kind of just check your answer as well.
Good, you can kind of check your answer as well. So this is us generating a probability distribution from a tree diagram. Not too bad? Alright, and clearly the contexts and questions will get more difficult, but fundamentally if you're asked for a discrete probability distribution, you need outcomes and the associated probabilities. Alright, on that note, this one is not a tree diagram one. You could do a tree diagram, but it'd be quite messy. A pair of dice are rolled. S denotes the sum of the top faces. Display the possible results in a table. So, if we're looking at S, the possible outcomes for a dice roll are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nothing too revolutionary. Find the probability distribution of S. So, you'll all seen a pair of dice rolled before, but many of you will not have memorized the probability distribution from 2 up. So, what tool could we use to get this probability distribution? Oh.
One of those fancy things we
Like find all the different outcomes?
Yeah, I would do what's called a two-way table. So this is dice 1, dice 2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And in theory, we can go through and write 1, 1. We could write 2, 1. We could write 1, 4, and so on. And we could fill out the table. And if we, and I'm not going to fill out the table because I think we can probably imagine in our heads. If we filled out the table, there would be 36 different outcomes. Yeah?
Yeah.
66. How many of those outcomes would add to 2?
1.
Lovely. So the probability of getting this is 1 out of 36. And same logic gets us that. There's only one way to get 12, it's down here.
So can you just come inwards?
Good. We're going to acknowledge they're going to be symmetrical when we come in. Then the question is, how many ways can we get a 3?
2.
Yeah, it's here and here, so 2 out of 36. Similarly here, 2 out of 36. And I know if you put in your calculator, or some of you will be tempted to abbreviate that to 1 out of 18. In the first instance, I would just keep it all out of 36. Because you know it's going to have to add to 36 on the top. So it can be nice to just keep the same common denominator. How many ways to get a 4?
3.
Good, there's 3. There's a 4 here, because that's 1, 3. There's a 2, 2, and there's a 1, 3 as well. So the 4s are there, and 3 out of 36.
The next one's going to be
We
4.
never got a set, I lost that back.
4 out of 36.
I just looked at the wrong.
Lovely.
So 7 is the most.
Yes. So there are more ways to make a 7 than any other number, because you've got 6 and 1, 5 and 2, 3 and 4, 4 and 3, etc. So there are 6 ways to make a 7. If you roll a pair of dice, 7 is the most likely outcome. Alright, so on that note, mode of the distribution, most likely outcome, 7. Easy. Find the probability that the sum is greater than or equal to 10. What's the probability it's greater than or equal to 10?
6 and 36.
6 out of 36, good, we add these. It's that plus that plus that. So 3, 2 and 1 is 6 on 36. You could write 1 on 6, but yeah, the sum of those 3. How's notes taking you? Am I going way too quick?
I thought it was just.
Alright, you can always rewatch the video if you want to take notes.
Take it.
Alright, expected value. Now, we're getting to the point where they might actually ask you questions like this in a SAT, which is more exciting. Expected value is something you guys will be very good at instinctively. For example, if we toss a coin 100 times, how many heads would we expect? 50. Like, we're expecting half to be heads. If we have a 1 in 20 chance of scoring a bullseye and throw 100 darts, 5. I'm expecting 5 darts. 5 darts to hit.
Oh, is that a SAT question?
Alright, so, I'll next get that. This gives us a very easy formula. On your next page, simple expectation is the expected number of outcomes is the probability times the number of trials. So if I told you it was a 1 in 20 of hitting the bullseye with 100 trials, you're in your head doing the 100 times 1 in 20 and getting out that 5. Or if I told you it's a 50% chance of flipping tails and you're doing 100 tosses, you're expecting 50, because in your head you're doing 100 tosses times 50, or times a half. So that is an intuitive equation that you guys have really seen before, and it simply gives us what is the expected outcome. Alright, there is more complicated expectation, which is this formula here. And it's one of those formulas that looks tricky until we actually practice using it. The expected outcome for a probability distribution is also known as the average outcome. So if I tossed 100 coins, on average, I would expect 50 heads. So we would often use the word...
Same thing as expected?
Yes, we would use the expected outcome interchangeably with the word average or mean. And the formula is adding up each outcome multiplied by its probability. Each outcome multiplied by its probability all the way up. And that looks tricky, but we'll do an example. So the expected outcome of this spinner. So if I was going to, play an arcade game here, and I was told that I would be paying $10 to play, does that feel like and you win the number of dollars on the face? Is $10 to play a good thing to play?
Yes. Yeah.
You're instinctively thinking yes. If I ask you to say it's $20 to play,
Yeah.
Yeah.
You break
Oh,
it
in
in
the
the middle.
maybe. So at some point there is that magic number where it's break even or it's fair. That's the average outcome. So the average outcome might not be one of these numbers, it might be in between a pair of them. And the way we determine average or expected outcome is we list the possible outcomes. So 5, 10, 15, 50. And each of these has an associated probability.
I literally put $49 something like that.
And the expected outcome, so the mean, is equal to the sum of all xi pi. which seems really strange, but we're adding up each outcome multiplied by its probability. So we are doing 10 times a quarter plus 15 times a quarter, I forgot 5, plus 5 times a quarter.
20.
It's gonna equal 10.
Goodness me, 5 times a quarter plus 50 times a quarter. And for this one here, you can effectively factor a quarter out.
Yeah, it's 20.
You can factor a quarter out, and then you have 10, 15, so 25, 30, 30 and 50 is 80, is 20. So,
So basically, you put $30.
so what this is saying is that if we pay $20 to play the game, we should play the game basically infinitely without gaining or losing. If the person running the game is charging us $15 to play the game, then we would expect to earn $5 per roll. If they're charging us $25 to play the game, on average we'd expect to lose $5 per roll. So the average is not necessarily what one of the outcomes is, but is effectively the weighted outcome. It's weighted by the probability. We'll do more examples.
What is the expected outcome? 20.
Yes, 20. Even though you can't roll a 20. Interestingly, does anyone know the expected outcome for a dice? Sorry, not the sum of 2 dice, just 1 dice.
1 and 6.
So 1 to 6. What is the average roll?
1, 2, 3, 4, 5, 6.
3.5.
Yes, it's 3.5.